All right, well, let me just get started and
I
I
can
trust that
tell you
everyone
have
can hear
26.
me.
You currently have 26 people.
Okay, wonderful. Welcome to this first joint UW Biostatistics Seminar of the year. It is an auspicious occasion. We know that is an auspicious occasion because we have fruit and banana bread in the refreshments corner, and not just coffee and water. And the reason it's auspicious is that we get to welcome Rebecca, who we have known for a long time. Fortunately for us, Rebecca did her PhD in the biostatistics program and has since been in multiple different places. And the one theme of wherever Rebecca is that she is a superstar. She was the recipient of the Magnuson Award. I'm sorry, I'm going to embarrass you a little bit. When she was a student here, she then transitioned to group health research, and which is now Kaiser. Kaiser North, no, it's not Washington, that's right. Really wonderful research group, and made her mark doing work with the Breast Cancer Surveillance Consortium, not just breast cancer, but in methods for diagnostic testing, and then transitioned to Penn, where she is currently not a faculty member in the biostatistics program, but also head of director of faculty development. Is that correct? Yeah. And of course, here she has made her mark with methods for analysis, really important and an area that's been growing so much and so critical over the last several years, analysis of electronic health record data, what can go wrong and how to make it right. That's not her title, but kind of is. Safeguarding medically underserved, so critical, vulnerable populations that we learned so much about during COVID in EHR-based research subject to informed presence bias. So Rebecca, welcome. It's really wonderful to have you. And let me know if you need tea or anything else. All right.
Thank you so much.
Yeah.
Thank you for the very kind introduction. It's so nice to be back here in Seattle and see so many friendly faces, and be visiting here at the Hutch, where I believe I gave a talk in the same room about 12 years ago. So it's nice to be back at long last. So as Ruth said, my work focuses on trying to make as much as we can from EHR data, use them for research to the best extent that we can, benefit from them while also avoiding all the pitfalls that come from using a data source that wasn't collected for research purposes, and hence is very messy and has a lot of limitations and challenges. And today I'm going to talk specifically about a challenge that arises when we try to use EHR data that have been differentially collected for different populations. So this is a topic that I've been thinking about for quite some time now, particularly the issue of dealing with data quality challenges in the analysis of EHR data. Recently, I was talking with a colleague about this, and I said I was going to get a student to work with me, and they said, "Can you find students who are interested in working on problems related to data quality? Doesn't that sound boring?" And I said, actually, it has become a very popular topic, among other reasons, because of the many uses that EHR-derived data were put to during the pandemic. So this is something I've been thinking about for a while. As EHR has proliferated and has become a more and more common resource for research, it has become a more popular topic. But I think the pandemic really catalyzed people's interest in using EHR data for research, because they realized it gives us the opportunity to study populations that we might not be able to otherwise reach, to do things at a pace that we might not otherwise be able to emulate using designed observational studies or clinical trials. So during the pandemic, there were a lot of perspective pieces and editorials written like this one from Forbes that were very breathlessly saying things like, big data is going to solve this public health crisis for us. And of course, that was hype and was very much overinflating the potential of what you can achieve using a very messy data source. But I think it really got people interested and excited, and it brought a lot of attention to the fact that these data are imperfect. And if we want to realize the potential of using them, we also have to grapple with the challenges. So the talk that I'm going to give today, I want to ground in two aspects of the challenge of working with EHR data. And I think these are illustrated by the concept of the learning health system. So the learning health system is another concept that has become increasingly popular in recent years. And it's basically this cyclical idea that when we are capturing data from routine clinical care in the EHR, we can take those data, we can conduct research on them, we can use that research to derive evidence about the best and most effective practices. We can then fold those practices back into practice so that patients are getting the best treatment currently known. And then we can collect data from that, roll it back into research, generate more evidence, and so on and so on. So we want to try to learn as much as we can from the clinical encounters that are taking place. When you think about research taking place as part of this cycle, I want to draw attention to two aspects of that cycle. And those are the two pieces that bookmark what we as statisticians are usually doing. So if we're kind of focused on that evidence section of the learning health system, I want to think about the data part. So where did the data come from? What was the process of patients receiving routine care that resulted in the generation of the data that we now have to use for research? And then on the other end, once we've produced our research results, what are they going to do with them? Exactly how is that evidence going to be incorporated into clinical practice, and how is that going to influence the care that patients receive? And so the point that I hope to stress throughout my talk today is that we as statisticians really have a role to play on both ends of that process. We're not just in the middle, plug and chug doing the data analysis. We need to think carefully about what data we're using and what biases it may encode. And then we need to think about how our research results are going to be used in practice and how that might perpetuate existing biases. So on the data side of things, the main source of bias that I'm going to be focusing on today is informed presence bias that arises due to the EHR data provenance process. EHR data provenance essentially refers to the data generating mechanism for EHR data. So in many ways, if we have a research database that's been constructed from EHR data, it looks a lot like a longitudinal observational cohort data set. However, the way that it was generated is very different from a traditional longitudinal cohort. And I think we need to understand that and think about where the data came from and what that implies in terms of measurement quality and missing data when we start to analyze the data. So on the right-hand side of this slide, I'm illustrating my version of the EHR data provenance process, which basically says in order for data to end up in the electronic health record down at the bottom, it has to go through sort of a funneling process. So the beginning of that process is the patient receiving care. An important thing to keep in mind is that in order to even get into the funnel, a patient has to access the healthcare system. So immediately there's a selection bias issue that results from differential access to care and differential willingness or ability to seek care across patients. Once a patient is in the system, they then have to have a clinical interaction that results in the generation of information that's related to the condition that we're actually interested in. And so we know that different patients receive care that looks different. Certain patients may be more likely to be referred for certain lab tests or radiologic imaging, and so on. So the specific data elements that are available for individual patients is going to be variable. The information has to be documented in a form that we can actually use. So everything that kind of either gets coded or typed up in a clinical note will be visible to us as researchers. Anything that just is a conversation between the patient and the provider that isn't documented essentially disappears into the ether. And then this will come up in the later part of my talk. There are also just frank errors in the EHR. So in addition to the information that's lost due to poor documentation, there are just mistakes that are made. There are things that are miscoded. There are things that are coded but don't actually represent true underlying clinical conditions. So at the end of the day, we end up with this record, which is clearly related to the health of the patient, but in an imperfect way. Importantly for the talk I'm going to give today is the fact that this record that we end up with looks very different for different patients. So for each patient, depending on their specific clinical needs, their ability to access the healthcare system, the way that the healthcare system chooses to interact with them, and so on, we're going to end up with slightly different information. And then also an important thing to keep in mind as we're thinking about constructing big networks and multi-site databases consisting of the data from multiple different healthcare systems is the fact that every provider, every clinic, every healthcare system has their own idiosyncrasies in terms of the way that they deliver care, and also in terms of the way they document care. So practices just in the way that things are coded. And all of that is potentially going to look like it means something in our records, but really just represents spurious documentation artifacts. And then finally, thinking about patients from historically underserved populations and vulnerable populations, if they have greater barriers to access, if they're less likely to be referred for more expensive tests, then that means the data that we have available for those patients will be fundamentally poorer quality. So what I'm really going to focus on most today is the fact that there's a different amount, a different intensity of interaction between the patient and the healthcare system across patients, which gives rise to differential data quality. So my presentation this morning, assuming I have, or this afternoon, assuming I have enough time, has 3 parts. In the first part, I'm just going to illustrate the challenge of informed presence bias, which results from this differential interaction between patients and the healthcare system. I'm then going to discuss a statistical approach to dealing with this challenge. And then finally, I'm going to talk about how this rears its head in the context of clinical risk prediction and possibly leads to problems with perpetuation of bias. So the first part of my talk is a set of results that were just sort of provocative that were generated by my former PhD student, Joanna Harton, in this paper from Journal of the American Medical Informatics Association. And you can see the title here. I like titles that have a colon in them. I think that that's fun. This one is a cautionary note. And that's really what this was. It was trying to raise awareness about this issue. And I think a lot of the things that I have to say about EHR are really along those lines, the lines of raising awareness so that we don't just naively analyze these data as if they came from any other observational database. So the specific problem of informative visit processes arises when our observation of a phenomenon is related to the underlying value of that phenomenon. So this is just an illustrative example. These are not real patient data. This is just to illustrate the point. But here I'm showing on the left 5 or 6 hypothetical trajectories for a biomarker where an individual patient's data is a different color. So we have a number of different patients here. We have a biomarker that's evolving in real time. We don't observe the biomarker evolving in real time because nobody is having their biomarkers measured every moment or hour or day. But what we observe in the EHR are discrete snapshots of the value that the biomarker takes. So on the right, I have an illustration of what our EHR measurement of this biomarker might look like if in between observations, we just interpolate with a flat line what we guess the value of the biomarker might be. So you can see we end up with this fairly chunky step function that sort of roughly traces the path that the biomarker is following, but loses a lot of the richness of that trajectory. But specifically, those trajectories that we observe in the EHR, we can decompose into 2 pieces. The trajectory that is composed of informative visits and the trajectory composed of non-informative visits. Here, informative visits occur because values of the biomarker that are high are more likely to result in the biomarker being observed. So this would be the case, for instance, if having a high biomarker value produces a symptom that leads to the patient seeking care. So in the slide previously where I had all visits, some of the visits were informative visits. They resulted from the fact that the biomarker was high. And so you can see in the trajectories that are just based on informative visits, we basically lose all of the information from the lower parts of the trajectories because they're unobserved. Patients don't come in for a visit when their biomarker is low. So we just observe this sort of skewed trajectory that only includes the high values. Fortunately, often in EHR data, we also have non-informative visits. So there will be cases where patients come in for well visits that it's unrelated to their current clinical condition. There'll also be cases where patients are being worked up for something unrelated to this specific condition, but as a byproduct of that workup, they'll also have the biomarker assessed. So in this example, let's say everybody comes in for a visit every 3 months. That's a very idealized setting, but let's say hypothetically, people are highly compliant. Everyone comes in for a visit every 3 months, so we're able to update their trajectories in a non-informative way quarterly. So the information that we observe from the EHR, we can break down into these two pieces, the non-informative visits and the informative visits. Yeah. That's a very good question. So the question is whether you can tell just from the data itself, which are the informative visits and which are the non-informative visits. The short answer is not from the biomarker alone, but you might have auxiliary data that helps you to figure that out. So I'm going to show an example in just a minute that looks like that. The problem of trying to analyze data that features this informative visit process is sort of twofold. So there's one piece that relates to measurement error, that we have this coarse, infrequent updating of the trajectory just from the medical visits. And then the second part is related to collider bias. So let's say there is some risk factor, such as family history of the condition of interest, that's associated with how frequently a patient visits the clinic. So patients who have a positive family history are more likely to make a clinic visit, are more likely to have their data updated. That same risk factor is also associated with the condition of interest. So when we conduct our analysis, if we only analyze the data that are observed at clinic visits, we're inherently conditioning on the fact that a clinic visit occurred, and therefore analyzing just those informative visits will lead to collider bias and will induce a spurious association between the biomarker and the health event of interest. I'm going to show a simple simulation study from this, this cautionary note that illustrates this issue. So we have a biomarker B that's evolving in real time. It varies over time according to this normal distribution with mean 0 and variance sigma. We have a binary covariate H, so you can think of that as being something like family history. And then we have a series of non-informative visits, and we're going to vary the rate at which those non-informative visits occur, whether they're quarterly or biannual or so on. We assume that the informative visits occur according to some process that's related to both the biomarker value and the family history. And then the health event of interest Y is also going to be related to both the biomarker and the family history or patient covariate age. So in the results I'm going to show on the next slide, we're just looking at variation in sigma, how big our step function moving around the patient-specific mean is, and then what the magnitude of the true association between the biomarker and the outcome is. These three plots from left to right are varying the magnitude of the true underlying association. So how strong is the relationship between the biomarker and the health event? And then within each panel, I'm varying how variable the patient's trajectory is from a small trajectory step size of 0.2 to a larger step size of 1. And then within each of those simulation scenarios, I'm looking at 4 different methods. So I'm looking at what our estimate would look like if we used all available values, so pooling together the informative visits and the non-informative visits, looking at just scheduled visits or non-informative visits, so just well visits that occur according to a fixed schedule, looking at just the informative visits, and then pooling them together and looking at all visits. Oh, the green plot, all values, is not all the visits, it's all the values. So if we truly knew the complete trajectory for a given patient. So I think an important point to make about this plot is on the left, where the trajectories are not very variable over time. We just have a step size of 0.2. We don't see a lot of bias across these methods, particularly when the true effect is small. In EHR data, you could spend days or years or probably a career talking about all the things that are wrong with them. And you could definitely convince yourself to never do any analysis at all, or that you need to do an analysis that accounts for every single possible statistical problem under the sun. So a really important thing when you go to undertake these analyses in practice is figuring out which are the important problems that require a sophisticated statistical method or a non-standard statistical method, and which are the problems that are maybe there in theory, but not in practice. So if we have a biomarker that's not varying a great deal over time, then it doesn't really matter how we handle this visit process. The biomarker is not changing that much. We can update the value occasionally, but we don't see a whole lot of bias. When you have a biomarker that does evolve more rapidly, how we handle the informative visits becomes a lot more important. So the observations that only use the scheduled visits don't suffer from the collider bias that results from conditioning on making a visit that's related to an underlying condition, an underlying patient characteristic of interest, but they're biased towards the null. Essentially, we have a measurement error problem. We're not updating the trajectory frequently enough. It's a coarse representation of the underlying true value of the patient. On the other hand, if we bring in the information from the informative visits, we see bias, in this case, in a positive direction. So we're now using a distorted and skewed version of what the patient's biomarker trajectory looks like. In this case, if we use all visits, we do a bit better because it's sort of balancing out the bias in one direction from the scheduled visits and the bias in the other direction from the informative visits, but that's not necessarily going to be the case, right? So that was a feature of this particular simulation setup because we happen to have the two biases going in opposite directions. But in general, that's not necessarily a good approach because we could have the bias in the informative visits going in the same direction as the bias in the scheduled visits. So finally, I just want to show an example of this in practice in real data. So we conducted a case study using data from the Children's Hospital of Philadelphia, in which we looked at the relationship between BMI and mortality in a pediatric population. The hypothesis was that low BMI would be a marker that the child was sick, maybe failure to thrive, and that it would be associated with higher mortality. We had a big data set. Often with EHR data, it's very easy to do a data pull and put together a very large database. We had about 70,000 kids in the database. And we observed right up front that patients who died had lower BMI Z-scores and also had more BMI measurements than children who survived. So it does look like there's a relationship between the overall health status of the patient and the intensity of measurement. So going back to the question of whether or not you can tell the difference between informative and non-informative visits, in this case, we tried to use information about the setting in which the measurement was taken as a proxy for whether or not the visit was non-informative. So we hypothesized that perhaps outpatient visits were more likely to be non-informative, maybe a good proportion of them represented well-child visits, whereas emergency department and inpatient visits were much more likely to have occurred in response to a health insult that the patient was experiencing. So in our data set of about 70,000 observations, we estimated a hazard ratio of 0.8 if we just pooled together all the visits. So it looked like, in general, higher BMI was associated with lower hazard of death, as we had expected. If we use all of the outpatient visits alone, we saw something similar. The majority of the visits are outpatient visits, so we would expect that estimate to be more similar to the all visits estimate. But we saw a little bit larger in magnitude estimate using just the outpatient visits. Whereas if we use the emergency and inpatient visits, we saw an estimate that was much closer to 1. So we think what's going on here is because of the direction of the informative presence bias in this sample, the emergency and inpatient visits, which are in response to a health insult that the patient has experienced, are substantially biased in the positive direction. So incorporating those into our analysis somewhat attenuates the results towards the null. That's sort of speculation as to what might be going on in that case. So I want to delve into that a little bit more and talk about how we can think systematically about the relationship between the intensity of patients utilizing the healthcare system and the data elements that we derive from EHR, and also demonstrate a quantitative bias analysis approach that we can use to try to figure out how sensitive our results are to this problem. Because as I said, sometimes it's really not going to be a big deal, and other times it's going to be pretty important. So as I mentioned before, this problem of informed presence essentially has two pieces. One is a measurement error or misclassification piece, and the other piece is collider bias due to conditioning on the intensity of utilization. So I'm going to introduce just a little bit of notation here that I'm going to use in the taxonomy for informed presence bias coming up in a couple slides, and want to emphasize that this is work that was led by my former postdoc, Molly John. She did a really, really thorough job in thinking through this taxonomy, so I want to make sure to give credit to her. So most of my thinking about what's going on in the EHR is predicated on this idea that what we see in the data is an imperfect reflection of what's actually going on with the patients. So we assume that there is a true exposure that we're interested in, X, and a true outcome, Y. Here, they're grayed out because they're latent. We never observe them. We're just going to try to get a sense of what they look like based on what we do observe in the EHR. I'm going to let N represent the intensity of utilization. This is the number of visits that a patient has with the healthcare system in some fixed window around baseline. And then XO and YO are going to represent misclassified analogs of X and Y. So these are our EHR-based variables that we derive from the healthcare data to try to make our best guess at what we think the exposure and outcome of the patient look like. And then finally, we have a vector of patient covariance Z, and I'm going to assume in the taxonomy I'm going to show in a moment that all of the relevant baseline characteristics are measured, and I'm going to assume that they're measured without error. We could add error to those as well, and then that would be even a bigger mess. But for the moment, I'm going to assume there are things that are well captured, like age, race, what cancer treatment a patient received, and so on. So I'm going to show example results for this setting using EHR data from the Flatiron Health Oncology EHR database. So Flatiron is a large network of EHR-derived data from oncology clinics all across the US. It's pooled together according to a common data model. Using data from Flatiron Health's metastatic breast cancer cohort, we wanted to answer the question of whether or not having diabetes is associated with progression-free survival in this set of patients who have metastatic breast cancer. So my exposure X here is diabetes. My outcome is progression-free survival. As I said, we don't observe any true health status in EHR. We observe imperfect proxies. So we don't observe diabetes, but we observe various things that tell us about the diabetes status of the patient, like maybe an ICD code for diabetes. In practice, we used ICD codes as well as biomarkers and prescription medications used to treat diabetes. So we have this imperfect EHR-derived diabetes measure. We also have what Flatiron calls real-world progression. So real-world progression is a measure of whether or not, based on what we're seeing in the data, we think that a patient has experienced cancer progression. I could give a whole separate talk, I think, about my concerns about real-world progression as a variable. I'm not going to go into that right at the moment, just to say it's very difficult to capture with high accuracy cancer progression using EHR data. So we have this exposure variable and outcome variable that definitely are related in some sense to the construct that we're interested in, but we know are imperfect. We also have a different depth of information for every single patient. So every patient has different utilization intensity. All of the arrows in this figure that are in red are things that we might hypothesize exist, relationships we might hypothesize exist, but we're not really sure. So perhaps patients with a greater burden of comorbidity like diabetes make more visits. So maybe there's a relationship between diabetes and utilization intensity. Maybe patients who are experiencing symptoms related to cancer progression have greater utilization intensity. Additionally, utilization intensity itself, N, is going to be related to what we see in the EHR. So I kind of think about it like this. Every time a patient touches the healthcare system, there is a non-zero probability of any diagnosis code being recorded for them. So hopefully the diagnosis codes that are most likely to be recorded are for the conditions that they actually have. But there's a good deal of misclassification in ICD codes. So utilization intensity is potentially related to the probability that someone has a diagnosis code for diabetes. Utilization intensity is also going to affect how well we capture various variables related to figuring out whether or not the patient has experienced progression. So all of these relationships might hypothetically exist. So we can think about this as depending on which of those relationships exist, we may have a case of differential or non-differential misclassification in our exposure or our outcome, and that misclassification may also be dependent or independent. So on this slide, I'm illustrating two examples of non-differential misclassification mechanisms. On the left-hand side, we're positing that there's no relationship between the true health conditions X and Y and utilization intensity. There's just a relationship between utilization intensity and whether or not we correctly classify the exposure. That's an example of a non-differential independent misclassification mechanism. The important thing about that is we know that in the case of a non-differential independent misclassification mechanism, bias is going to be towards the null. I don't think that bias towards the null is necessarily something that we should ignore and not be worried about. But if we're thinking about using EHR to screen for possible signals of relationships between conditions that may be of concern, we may be less concerned about bias towards the null than other forms of bias. On the right-hand side, I have an example of a non-differential dependent misclassification mechanism. So here, utilization intensity N is associated with both our misclassified exposure and our misclassified outcome. So that means the accuracy of both X and Y are going to be correlated, and therefore this is a dependent misclassification mechanism, which means bias could be towards the null or away from the null. So if we think that non-differential independent misclassification is less concerning, a simple thing we could do is say, let's condition on N. So when I put a box around a variable, that means in my analysis, I'm going to condition on it. Here I'm saying, let's condition on utilization intensity. So that will convert the non-differential dependent misclassification mechanism into a non-differential independent misclassification mechanism conditional on utilization intensity. I still don't think that's great, but maybe it's a little bit less concerning than bias could be in any direction. This idea of conditioning on utilization intensity is one that's pretty prominent in the epi literature. In this field, it's definitely a thing that people do. And this is the reason why. They think that non-differential independent misclassification is less concerning than potentially anti-conservative bias. In the case of differential misclassification, we're just going to add one additional relationship to the DAGs that I had on the previous slide. So here we're going to posit an additional relationship between the outcome of interest Y and utilization intensity. So by doing that, there's now a relationship between Y and the accuracy of X. So now we have differential outcome dependent misclassification in our exposure X. And so just like the dependent misclassification, that can lead to anti-conservative bias. On the right-hand side, we have both problems. We have both the differential misclassification of X and we have dependent misclassification of X and Y. And again, conditioning on N would convert both of those mechanisms to conditionally independent non-differential misclassification. So finally, this is the catch-22 of this entire problem. Even if we thought that it was a good idea to condition on N to get back to a case of non-differential independent misclassification, if N depends on both X and Y, then conditioning on N induces a spurious association due to collider bias between the exposure and the outcome. So now not only do we have resultant bias from the residual non-differential independent misclassification, but we've added additional bias due to the collider bias. In practice, we don't know, right? So we can look at the DAG, like I showed you for the relationship between diabetes and progression-free survival, and we can hypothesize which relationships we think are plausible and which we think are implausible. But we truly don't know what the set of underlying relationships are. So we proposed a quantitative bias analysis approach to try to assess the sensitivity of your estimates to these different misclassification mechanisms. This adapts an approach proposed by Lyles and Lin as Statistics in Medicine paper from 2010, which is looking at the problem of differential misclassification in an exposure X, where its accuracy depends on a covariate Z and the outcome Y. So they propose to use a predictive value weighting approach to try to get a sense of how sensitive results are to these misclassification mechanisms. Doing this is really, really straightforward. So I love things that are really straightforward because I think we're about 1,000 times more likely to actually use them than things that require specialized software. So this is a straightforward approach that you can implement in standard software to get a sense of how sensitive your results are. So all we're going to do is take each observation in the data set. We're going to replicate it. And for each replication, we're going to set the unknown variable equal to each of the possible values that it could take. So in this example, if I'm thinking about just misclassification in X, I would replicate observations. I would set one replicate equal to X equals 0 and one replicate equal to X equal 1. I then weight each of those replicates by the posterior probability that that is the true X value. So if I think the true X value is related to both the outcome Y and a set of covariates Z, I would weight it according to a probability that looks like this, which is basically the PPV for a person with the observed XO, given a known sensitivity and specificity for XO. In the informed presence bias context that I'm talking about, rather than conditioning these probabilities on covariates Z, I'm going to condition them on utilization intensity N. So I'm going to replicate all of my observations. I'm going to assign these weights that are essentially how likely do I think it is that this is the true value for X. And then I can undertake estimation just using standard software, like in this case, a weighted logistic regression. That's a quick summary of the Lyles and Lin sensitivity analysis approach. In the case that I'm talking about, where we have both misclassification in X and misclassification in Y, it gets a bit more complicated, but the basic idea and the implementation is the same. We're going to replicate the observations. We're going to set X and Y equal to hypothesized true values, and then we're going to weight those observations by the PPV, or the posterior probability that those actually are the true values for that observation.
How do you do for both though? I mean, the probability X equals X and Y equals Y?
Yeah. So it can be a little bit tedious to go through and derive all of those probabilities, but it can be done and is relatively straightforward if we know the sensitivity and specificity of X and Y conditional on N. That's not something that probably anyone anywhere actually knows. I think at lunch, we were talking about validation studies in EHR data and the fact that all of these variables that we're deriving are imperfect and really should be validated. And I was saying, in my experience, sometimes people do that validation and sometimes they don't. Sometimes they just rely on their clinical sense that the variables are probably reasonably reliable. Even in the best case scenario where people actually do that validation study, no one is doing the validation study conditional on additional characteristics, particularly not conditional on utilization intensity. I can confidently say that in my career, I've seen that exactly 0 times. So in practice, if we knew sensitivity and specificity conditional on N, we could actually come up with unbiased estimates for our association parameters. Since we don't know them, what we're going to need to do is evaluate how much our association parameter estimate varies across a range of hypothesized plausible values for sensitivity and specificity. This is just a really quick simulation study. Just essentially, this slide is just to say this does actually work if you know the true sensitivity and specificity. So here for the set of different misclassification mechanisms that I showed you, I'm demonstrating that the naive method is biased. The covariate adjusted approach where we condition on N is biased. If we knew the true sensitivity and specificity of X and Y conditional on N, and we plugged them into that predictive value weighting approach, we would get the blue estimate here, which does remove the bias. One point I additionally want to make about this is the blue bar shows that we do successfully remove the bias across all of these misclassification mechanisms. It also has very inflated standard errors relative to the other two approaches. And I would argue that that is a feature of this method, not a bug, because if we think that we really don't know what X and Y actually are, probably our estimates should reflect that uncertainty. And the naive estimate is certainly spuriously precise. And then finally, I just wanted to show you what the quantitative bias analysis version of that looks like for our case study, looking at the relationship between diabetes and progression-free survival. So when we took the data and just looked at the raw unadjusted association between EHR captured diabetes and progression or death within 1 year, the odds ratio for that association was 1.08. If we additionally adjust for N, the odds ratio is attenuated to 1.04. So we then undertook the quantitative bias analysis where we varied the sensitivity and specificity of X and Y for people who we classified as low utilization intensity or high utilization intensity, just based on dichotomizing them at the median baseline utilization. And a very, very quick high-level summary of these results would be to say, we observe something relatively similar. So moderate, low to moderate strength of association between diabetes and cancer progression or death across the grid of values that we looked at, except for this top row, which is the case where sensitivity for Y for people who were low utilization intensity individuals is very, very high. And sensitivity for X in those same low utilization individuals is low. And that, I think, is a pretty implausible case. So across the grid of values that we looked at, we felt relatively confident that this estimate was robust to misclassification. So finally, in my remaining time, I'm going to switch tracks a little bit and just show you an example of how these differential data capture issues potentially trickle down into clinical risk prediction and potentially perpetuate biases in EHR-derived research. As Ruth mentioned, a lot of my work is with the Breast Cancer Surveillance Consortium and has focused on breast cancer risk prediction. In the context of breast cancer risk prediction, we might be interested in undertaking a personalized medicine approach. So personalized medicine says we should be delivering care that is tailored to each patient's individual characteristics and needs so that each patient gets the care that is most appropriate for them. In the context of cancer screening, that would mean tailoring our cancer screening regimen. So maybe that's changing the starting age for screening, the stopping age, the frequency, the modality that we're using. I think this is, on the surface, a very appealing idea. It suggests the right people are getting the right care. That's a good thing. In practice, the devil is in the details because this personalization is going to be carried out using risk prediction models that we create and which are imperfect. And in the case of EHR-derived risk prediction models, I think there are a number of additional sources of concern. One is that individuals who are medically underserved and those who are from historically marginalized communities will be underrepresented in the data sets that we use to develop these risk prediction models. So our risk prediction models don't necessarily perform well in those underserved populations. If our models incorporate genetic risk factors, polygenic risk scores, and those models were developed primarily in European populations, then they may not apply to racial and ethnic minority groups. as I've been talking about, there are all sorts of complex patterns of care that affect what data we have access to and analyze, and there are historical patterns of inequitable care delivery across populations. We know that not everyone receives care that looks the same. This trickles down into the quality of the data that we have available to analyze. So we may have systematically poorer data quality for medically underserved and marginalized populations. So all of these things interact with each other and act together to result in the potential for poorer risk prediction models and therefore less usefully personalized care for disadvantaged and vulnerable individuals. So I'm going to quickly show you some results of a risk prediction model that I developed with Yuver Su, who's in the audience today. So this is really her work, which I'm presenting on her behalf, to look at surveillance failure in women with a prior breast cancer. So the idea here is that once a woman has experienced a first breast cancer diagnosis, she's going to come back for periodic surveillance mammograms to look for a second cancer. Some of those mammograms will be what we call surveillance failures, which means that the woman had experienced a second breast cancer, but the mammogram is negative. So those are missed cancers or false negative mammograms. We conducted this study in the BCSC, which is a large national registry consisting of linked radiology information on mammograms and cancer registry and pathology data, which tells us about the occurrence of second cancers. This gets back to the very beginning of my talk when I was talking about the learning healthcare system and thinking about the way that our data are going to be used. So we know that risk prediction modeling is not a neutral exercise. It specifically has implications for patient care and potentially policy implications. So in the case of this surveillance failure risk model, the thought was that women who are at high risk of having their second cancer missed by a surveillance mammogram should possibly be triaged to more intensive surveillance. So maybe they should be coming in at a shorter interval, maybe they should be getting an MRI instead of a mammogram. So that means that if our risk prediction model says that someone is at high risk of a surveillance failure, they potentially are going to get access to additional resources that would not be available to a lower risk individual. So that means this is not a neutral activity. This has direct implications for the care that people receive. So we compared a suite of alternative risk prediction models for this task applied to the BCSC data. These were a combination of traditional statistical approaches, regularized regression, and some newer machine learning approaches. We evaluated performance overall, and we were also interested in performance within individual race and ethnicity subgroups because we were particularly concerned about this issue. What if our model doesn't work as well for women from racial and ethnic minority groups? Does that potentially perpetuate inequities or result in loss of access to resources? A quick point that I want to make is that there's a lot of interest right now in algorithmic fairness, in making sure that we are not perpetuating biases and not carrying out activities that lead to inequitable care. But an ongoing challenge is the fact that racial and ethnic minority groups are significantly underrepresented in many research databases. So in this example, our database included about 10,000 mammograms overall. About 7,500 of them were in non-Hispanic white women. A small subset were in women of other racial and ethnic backgrounds. And if you look at not just the total sample size, but the number that actually experienced a surveillance failure, you can see that the sample size gets quite small. So right off the bat, this is a difficult thing to do. So for each of the models, we looked at calibration in the overall population. And you can see here across these three different measures of the calibration of our prediction model, some of the models were well calibrated, some of the models were not well calibrated. For those that were well calibrated, we then looked at discriminatory accuracy. Here are ROC curves for 4 of the well calibrated models. The machine learning methods and the regularized regression methods performed very, very similarly. They all had AUC of around 0.63. We then stratified our calibration results by race and ethnicity to see if we could investigate this question of whether or not the models were performing similarly for women of different racial and ethnic backgrounds. I looked at this plot for some time trying to decide if I thought there was any evidence of inequity. And what I conclude is that the models that perform, that are poorly calibrated overall are poorly calibrated in at least some race and ethnicity subgroups. The models that are well calibrated overall are generally well calibrated across the race and ethnicity subgroups. However, we've completely lost from this figure a few of our racial groups as well as Hispanic women. Because of the small sample sizes, we just weren't able to undertake this exercise in those groups. And more important, going back to the main theme of my talk, I was particularly concerned that we were systematically failing to capture outcomes for women from more disadvantaged groups. So what if our model appears to be well calibrated based on the data that we have, but we're systematically less likely to have accurately captured second cancer diagnoses for women from some of these groups? So to investigate that question, I undertook a simulation study where we took the data on this topic from the BCSC. We used that as inputs, and then we generated data which resembled the original BCSC data, but either added or subtracted relationships between race and ethnicity and downstream mammography outcomes and cancer. So at the bottom of the slide, I have a figure that illustrates the overall idea, which is that race and ethnicity only impact second cancer and mammography performance through downstream effects on social determinants of health, second cancer, and primary tumor and treatment characteristics. So there's no direct relationship between race and ethnicity and the outcomes that we're interested in. In our simulated data, I then systematically removed relationships between race and ethnicity and some of these downstream factors, looked at knocking out the relationship between race and social determinants of health, or between race and primary tumor and treatment characteristics. And then we looked at what the results were in terms of both mammography performance and also the results of our risk prediction models applied to this population. So I'm going to show you results of how our risk prediction models look if we use them to make a decision about which individuals should get additional surveillance imaging. An important point is that the risk models that I used in this context do not include race and ethnicity. So that's not part of the prediction model. These are hypothetically race agnostic risk prediction models. So if we apply a model for surveillance failure risk, which does not include race and ethnicity, to our simulated data that were generated to mimic the BCSC data, but add or subtract relationships with race and ethnicity, and then we look at the proportion of women who are recommended to receive supplemental surveillance imaging by race, what we see is big differences by race. So this makes sense. If the distribution of any characteristics that are in that surveillance failure risk model vary by race, then the risk distribution is going to be different by race. And the implications of applying that model in terms of who is recommended to receive supplemental imaging will also be different. The most notable thing here, I think, is that a much higher proportion of Black women would receive a supplemental imaging recommendation if we used this race agnostic surveillance failure risk model to make the recommendation. And that's true regardless of whether we constrained the simulated data to include or exclude relationships between race and cancer characteristics or race and social determinants of health. Then on the right-hand side, the very last thing that I did was to say, what if data quality also varied by race? So what if our ascertainment of second cancers is systematically poorer for some race and ethnicity subgroups? And at least in this context, reassuringly, that made relatively little difference. So my concern was that when we introduced this data quality variation, we'd suddenly no longer see a higher proportion of Black women recommended to receive surveillance failure. And in practice, that is not what we observed. And then just very quickly, this is an analogous exercise, but where we make the recommendation for supplemental surveillance imaging based on predicted second cancer risk instead of predicted surveillance failure risk. And you can see that the pattern by race and ethnicity here is completely different. So when we use a different risk model to guide our predictions, now a lower proportion of Asian Pacific Islander and Hispanic women receive supplemental imaging recommendations. We no longer see that much higher proportion of Black women receiving a supplemental imaging recommendation. I'm I'm not drawing any conclusions about that in terms of saying that one is better or one is worse, simply illustrating that if we use different approaches for personalizing care, we get very different answers. And the implications in terms of different patterns of care for women from different racial and ethnic groups potentially looks really different. So I will wrap that up just by saying there is a lot of interest and a lot of thinking right now in algorithmic fairness. And I think in that thinking, we really need to connect it to the downstream outcomes that result from the implication of our models. So many of the papers that are out there on algorithmic fairness look like we did at calibration or at measures of accuracy by race and ethnicity. But you can have a model that performs exactly the same across race and ethnicity groups, but still translates into very, very racially disparate implications in terms of the care that it results in. So I'm right at time, so I will wrap up by saying, I think there's lots of potential and also lots of pitfalls in using healthcare-derived data for research. I think it's going to, no one's going to stop doing it. We're going to be doing more and more of this kind of research using passively collected secondary data from sources like clinical care. Those data were not created in a vacuum. They were created by human processes that are filled with all sorts of bias, all sorts of idiosyncrasies, all sorts of error. They're messy processes. And I think we do ourselves a disservice as statisticians when we analyze them as if they just sprung from the earth perfectly formed, and we're not going to engage in the process of figuring out where they came from and what challenges they produce. So hopefully I've encouraged everyone to think carefully about the data that we're analyzing and also to be part of the process of thinking through how the evidence we generate will be used, because we understand our results better than anyone else. I don't want to just blindly hand them off to someone who will make use of the data without being part of that conversation. So hopefully we'll all participate in that conversation, claim our seat at the table, and not just be cogs in the machine cranking the crank of R or Python, but taking an active role. Thank you.
A couple of questions? Yes. Yeah, so many questions, so little time. Let's take advantage of having Rebecca here to, please feel free, audience and online, the way they've set it up. Let's see if I can even see the chat online. I stop share. Anyone, there we go. Folks online, feel free to post questions in the chat. I can see the screen. So let's open the floor for questions. Yeah.
I had a question about the second part of your talk where you talked about the bias. When you're talking about incorporating the sensitivity and specificity, but hopefully the known sensitivity and specificity of X and Y, just to make sure I understand. So that's having some sort of previous data on, like, if someone has a diabetes diagnosis in the EHR data, for instance, how well does that match reality of whether they have diabetes and say the progression of survival?
Yeah, that's right. That's exactly what I'm referring to. And it could be from, so there are databases that are just like operating characteristics of EHR-based algorithms. So it could be something like that, like I'm using a validated algorithm and this is what the sensitivity and specificity are. Or it could be in your own current data set. So, you could do a chart review and validate some subset of the observations to get that information.
Yeah, I was gonna ask where that data from generally.
It's really, really tricky. And like I'm sort of like glossing over how difficult that actually is to do. And the fact that it's a little bit circular to say we're going to validate an EHR derived measure using EHR data, right? So that's what people standardly do. For instance, if you want to validate an algorithm for diabetes based on diagnosis codes and biomarkers, the way you would do it is to conduct a chart review and have trained abstractors look at the chart and try to figure out whether or not someone actually has diabetes. For some conditions, that might be a reasonable thing that you can deduce. I worked on a study at Group Health years ago where we were looking at fracture. We wanted to see how well fracture codes corresponded to whether or not someone actually had a fracture. And it made sense to have an abstractor look at the chart, see if they could find an image that showed a broken bone. In some cases, you're just as likely to not have captured the code as to have not captured any other information about the condition. And in that case, even doing the chart review is sort of a silver standard at best. Yeah. So the question is what measure of algorithmic fairness do we think was best? I truly don't know. So I've looked at, I've done this sort of exercise where we construct a clinical risk prediction model, and then we look at whether sensitivity and specificity or calibration are equal across races. I don't know how useful that is because it's, I'm not sure it's necessary or sufficient. It's definitely not sufficient. It may or may not be necessary. The point that I made at the end there about looking at downstream outcomes, that's kind of the thing that I can't get away from. I feel like ultimately none of it matters unless we think about the way the risk prediction model is going to be used. And how that's going to translate into differences in outcomes across groups. So, as I think it's a reasonable standard practice to see if accuracy and calibration are different by race and ethnicity. And that's what we did in that study. But given that it's not sufficient, I feel like that's sort of the beginning and not the end.
Question, okay. Okay, Katie has a question about how to deal with missing data for EHR, where so much of the missingness is informative. And in a sense, the informative presence is sort of is it the flip side of informative missingness? And how, and if not, if so, and if not, how would you answer the question?
Yeah, it's a really good question. So the informative presence bias issue that I'm talking about is a form of informative missingness, or anyway, it can rear its head in the form of informative missingness. So the best that I think that we can do in that setting is using sensitivity analysis type approaches like what I described, or other sensitivity analysis approaches for MNAR missingness. Or, I mean, what would be ideal is if we could convert the MNAR missingness problem into an MAR missing problem. So if there is a variable that helps us to deduce whether or not somebody's going to have missing data. I worked on a project with Flatiron EHR data where we were looking at outcomes of a particular cancer treatment regimen, and we observed that an very important predictor, ECOG performance status, was missing in a large proportion of patients, like 50% of patients. And the oncologists that I collaborate with said, we're concerned that this is MNAR missingness because we think patients with very poor performance status are not supposed to receive any treatment at all. And so their treating provider is less likely to record the fact that they are poor performance status because they want to continue to treat them. And when they told me that, it was like alarm sounds, like, oh gosh, like we've been using multiple mutation to deal with missingness, assuming it was MAR. What do you even do in this case? So I do have a paper in epidemiology where we investigated different multiple imputation strategies to try to deal with this. The short version is there are some papers out there that say certain machine learning approaches may be able to handle MNAR missingness. Okay, yes, Yates is shaking their head appropriately because this is a sketchy claim, and that's how I felt about this as well. However, the one part of it that's not sketchy is if we have a really large database with many predictors, which are all very correlated, and MNAR missing this mechanism in which the value of the variable itself is associated with whether or not it's missing, may be sort of weakly MAR if that variable is highly correlated with a bunch of other variables. So in my epidemiology paper, we did not find that these machine learning multiple imputation methods could deal with MNAR missings. They did not work. And I think that's because we were in sort of a standard epidemiologic setting with about 20 features. There wasn't a ton of correlation among them. I'm skeptical of the machine learning papers out there that claim that this does work, but I want to at least hypothesize that in high dimensional settings, I'm giving the benefit of the doubt to the people who publish that work and saying, if you have a really high dimensional setting with a lot of informative correlated features, you may be able to convert and what appears to be an MNAR missing this problem into a sort of approximately MAR missing problem. That's the best I can
So
do,
long as all those features don't happen from the presence bias.
which they all do.
All right, we're going to close. Rebecca will be around for a few minutes. If there are remaining questions, thank our speaker, thank the audience. And look forward to the next joint UW Biostat